concepts which have already been covered in the lecture. Anywhere you feel you have got any doubt, please you can interject and you can ask me. And due to this reason, because I have to cover both the weeks, so I shall cover both the concepts at a fast pace. Now we know that in week 5 there are no PAs, so I will not be touching upon the PAs. However, I will take some questions related to the week 5 concepts from the previous question papers, quiz papers. And in the week 6, okay, I shall try to solve the PAs also, which are tricky. So before we start with the week 5, I shall revise the concepts of momentum-based gradient descent and the Nesterov accelerator. So how did we arrive at MGD? What we wanted to achieve? Basically, we wanted to achieve that the convergence of the algorithm should take place. It means that at the gentle surfaces, the updates they were slow. At the steep in the steep regions, the updates were more. So how to navigate through those gentle surfaces? We came with an idea of momentum-based gradient descent, where we took the momentum from the past, and that's why you can see on my screen the MGD update rule. A beta was introduced, and when you expand this, you will realize that as we keep on going in future, the relevance of this W1, W2, it keeps on vanishing. So that was the basic idea of MGD. Now, due to this momentum built up, this algorithm the used to oscillate. It used to pass the local minima, then again come back. Then so it was oscillating at the local minima. So to solve that, Nesterov somewhere in 1983 he gave an idea of accelerator, that when you compute the gradient, you compute taking this future position in account and then you navigate. So these were the basic ideas of MGD and Nesterov accelerator. So these are also optimizers. Optimizers are the how to make the algorithm faster. So those are the optimizers. So we can consider that MGD and NAG are also the optimizers. Now in the week 5, the concept came for the sparse parameters, because there might be a lot of data sets, especially the image data sets, where few parameters they are very sparse. Sparse means that they have got high values of zeros and very less values of ones. So in this case, what happens that in case of sparse parameters, the updates are less. Why the updates are less? Because we know the formula for delta W. I shall just write here. Delta LW is dependent on X. So if X is 0, then this is 0, and very few updates for this sparse parameter. So in the lectures, certain diagrams, certain contours they have been given, certain examples have been given, that for example, this is a dense parameter and this is a sparse parameter and these are the weights. So for the updates will take place for the dense parameter, and in the last only the updates take place for the sparse. Now to solve this problem, the idea came that very similar to the momentum one, where we were taking the weights, accumulating the weights, and we were taking them. Here we take the square of the gradient in future. The update rule is as shown on the slide, and the algorithm was called ADAGRAD, that is adaptive gradient. So this gradient, when we see, this gradient is accumulating over a period of time. So what happens, this effective learning rate which is there, this VT keeps on increasing, this denominator keeps on increasing, and this effective rate of learning, it keeps on decreasing. So by this, what happens that we are accumulating this gradient square. So your update for the sparse parameter takes place. However, for the dense parameter, this value rapidly decays. So this is the disadvantage of ADAGRAD. Now, to solve this problem, that how to do that, the second algorithm came was the RMS prop. In RMS prop, we can see that in ADAGRAD, okay, there is no beta. So these gradients which are there, they are adding up to WT square. So idea like in the MGD, we took the beta, so we take only one portion, like some portion of that, and the RMS prop came. So what happened due to this, that this effective learning rate which is there, now its decay is slower because this value is not increasing as it was increasing in RWA. However, still there is a rapid decay. So RMS prop converges faster than the autograd, but still that, like I mentioned, the problem of decay remains for the dense parameter. Now, how to solve it? So to solve that, before we proceed further, I shall just cover certain points of autograd and RMS prop. That in autograd, the learning rate monotonically decreases. In case of RMS prop, the learning rate may increase, decrease, or remains constant due to the moving average of gradients in the denominator. However, in both of them, the decay is taking place and both are sensitive to learning rate. So if we have selected some learning rate which is not appropriate for that data set, then it is sensitive. So one solution is that if we don't want to decay, then we have to remove this learning rate. So with that, the algorithm came ADA delta, that is adaptive delta. So in this ADA delta, there is no initial learning rate. And there are two values, one is UT and one is VT. VT is one step ahead of the UT. So if I take you like this, if these are the values, VT is here and UT is always one step behind VT. And we calculate like in the RMS prop, we had delta WT square, we have got beta, but there is no N. We are having this UT and gradient of WT is UT minus 1 plus epsilon square root divided by VT plus epsilon gradient of WT. Now by this ADA delta, what happens when we are in the steep regions? So you can see on my screen, when we are on the steep regions, the VT will be more than UT. And due to which this, when this denominator is higher than this, so this will be less than 1. So in the steep region, there will be less updates. However, as we cross from the steep region to gentle region, now here is the place where VT will become lesser than UT. So when denominator becomes lesser, then this is more than 1 and there are more updates. So this is adapted, that the learning rate is now getting adapted as per the surfaces, as per the steep and the gentle. So this is a very, very effective algorithm which overcomes the disadvantages of both ADA-grad and RMS prop. I will suggest to all the students, please go through the slides 30 to 34 thoroughly to understand this. What I've covered just in a short form, this steep region and gentle region. Professor has explained in detail how this is happening. So I'll request everyone to go through the slides. Now, so we can say that ADA delta, it converges faster than RMS prop, and RMS prop converges faster than ADA-grad, but RMS prop and ADA-grad both depend on eta. Now next concept came, we have reached ADA delta, we have solved the problem of those gradient descents and the learning rate. The next concept came that like MGD, why don't we add this momentum into ADA delta? And with this, the algorithm came ADAM, and in 90% of the, mostly 90% all over, this ADAM is the default optimizer. If you will go to any site, you will see mostly ADAM is used. So in ADAM, we add this momentum. You can see this is similar to your momentum. This we retain from the RMS prop. And what we do, we do the bias correction for MT and VT both by MT divided by 1 minus beta 1t and VT minus 1 minus beta 2t. The reason for this has been covered in the lectures by the professor. I'll request again all of you to go through that, why this bias correction takes place. But I will just cover in short form that if you don't do the bias correction, then your initial updates, they are very, very large. When you do the bias correction, they start from the same region. However, please remember that whether you do bias correction or you don't do bias correction, still your convergence will take place. Okay, we do bias correction only to make the first updates which are there lesser. So a lack of initialization of bias correction would lead to initial steps that are much larger, which has been shown in this figure. Okay, till now, any doubt, any clarification anyone has?
I have a question, the previous one, not Adam.
Okay.
This beta, how can we use beta to alter the behavior? That
Uh,
this history one is the current gradient, right? Will it make a difference how on the beta value?
okay, this beta which is there, this beta we have taken from the RMS Pro.
Okay.
What was
Right.
happening? Yeah, I'll just add the one page. See, what was happening in ADA grade? We were taking, for example, W1 square plus W2 square plus up to. So they were constantly increasing. Now, when we add this beta, which is generally 0.9 into Bt minus 1 plus 1 minus beta into Wt square. Now, what happens when you now this increase, which is not uniform. It is not monotonically increasing.
Yes.
When you will expand this formula, it will come somewhere 1 minus beta, then uh, 2 0 to t, then some figure is there. When you expand this, so this increase which is there, we have reduced this increase, and like which we did in like MGD, the effect of this W1 squared now diminishes as we keep on going. As we keep on moving forward, the effects of the initial gradients which are there, it keeps on decreasing. So,
but we are not changing beta, right? Beta is remaining 0.9 throughout.
See, beta will remain throughout, but okay, for example, I'll give you an example. Just again.
Right.
Let's take Vt minus 1 is equal to 0. Take W1 is equal to W1. Okay?
Okay.
So your V1 will become, or V0 will become W1 square.
Yes.
And 1 minus beta. So this is 0.1 of W1 square.
Yes.
In this case, it was this. Okay.
Right.
Now, when we go to V1, it becomes beta into this 0.1.
Okay, so 0.09 now, right?
Okay. Now
Right.
to W2 square. Now you can see this again has become 0.09 of W1 square.
Right.
Okay, 0.1 of W2 square. So like as we keep on moving forward,
Okay.
we are not taking the entire, whereas in this okay, we are taking the entire. So
Okay. So the history has less
yeah,
value. That's why
less.
the current gradient will decide the
Yes,
beta rate.
yes. Okay, so that's why the decay which was there, and by this the Vt plus eta, this is not increasing as faster, which was increasing again in that case. Okay.
Got it.
Yeah.
Okay.
So that is the basic intuition. So this Adam case covered.
Brilliant.
And, okay. Then now from Adam then we took why not to combine NAG also. So Nesterov when we took then we came with the concept of NADAM. So it is called. And then the third concept came that why we are taking this gradient square. Why not to take maximum of WT? We want to basically, there is a sparse parameter. So why not to take from his history what is the maximum gradient which has been calculated instead of squaring. So with that, this RMS max prop for the RMS came for the ADAMX, this thing came, and then I have covered for the NAD. Okay, NADM you can go through. There is a slight difference between the NAG and NADM. Slight difference. In NAG, if you will see the update rule, I'll just cover it here only. In NAG, this value which is there, beta u2 minus 1, you're computing here also and you're computing here also. In NADM, okay, it is done only once. Okay, those algorithms are there in that, and once I will prepare this document into PDF, I will share some links of the Colab files which I have prepared myself for the AdaGrad, ADAM, for the RMS prop and ADA Delta. So those links will be there. You can go through those Colab files. They'll help you. Okay, so this was all about the optimizers. So we can see the optimizers which are there. So optimizers we saw in one of the question in the previous quizzes. There was a question whether MGD is an optimizer or not. So I hope now it is clear that they are also the optimizers. So we came to AdaGrad. Then we came from AdaGrad to RMS prop. Please know the characteristics of these algorithms because there might be some questions on the concepts which are being used in this. Ada Delta, what are the advantages, what are the disadvantages, then ADAM, then we came to NADAM, then we came to RMS max, and there is a ADA max, which is basically ADAM but taking the max values. And finally, the learning rate schemes, they have been correlated in this slide. So with this, week 5 main concepts are covered. Now I will just cover some questions which I have taken from the previous quizzes, that what kind of questions you can expect based on the concepts. For example, I hope my screen is clearly visible. Are you able to read the screen?
Yes, good for me.
Yeah. So assume that we are updating the weight and bias of a neuron using the AdaGrad optimization. So this is the AdaGrad formula has been given, where nu naught is the initial learning rate and v minus 1 is equal to 0. The plot below shows the change in learning rate over iterations. The blue curve represents the changing learning rate for weight, and the red curve represents the change in learning for bias. Now, there are certain statements. There is a statement that the gradient of the weight W changes slowly as compared to the gradient of the bias B if we move on the contours of the loss surface in the direction parallel to the weight. Will it be true or false? Anyone?
Parallel to the weight, there should be no change, no?
Okay, not parallel. Okay. Basically, they are asking that which one will change slowly and which one will change fast.
Okay, I thought more perpendicular means faster, right? Bigger steps, more gradient.
So basically, I'll just tell you, this is like the surface, loss surface.
Right.
This is the loss surface. So we can see that this is if this is W1, W2. So W1, you can see it is a sparse.
Right.
This is dense. This is dense. Okay.
Mm-hmm.
So first of all, by AdaGrad, so your gradient will converge.
Yeah.
Okay.
Right. It will not move around because of the weight.
But in the AdaGrad, what we saw that this effective learning rate which is there,
mm-hmm.
for the dense parameters, it decays.
Right. So steps will be bigger.
Yeah.
Right. Okay. So momentum will be higher then. Okay.
Yeah, yes. And for this part, it will be gradual.
Right.
That is the basic question. So we can see that weight W what they have written, changing weight and bias. So weight is a sparse parameter, we can say. So it will be true that for the sparse parameter, the weight W will change slowly, whereas for the bias is dense, it will change rapidly.
Right. If weight is sparse and right. Okay.
Yeah.
Right.
And the statement that the algorithm converges to the local or global minima after 500 iterations, we can see that both, effective learning rate for W and B, it
Right.
is
They
it is
become
becoming
constant.
somewhere around 300. So it is
Right.
convergent. Okay.
Right.
Okay, so these are the kind of questions you can expect in the quizzes, basically on the concepts. What is ADA grade? How does it function? What are the disadvantages? Then to overcome that, we arrived at RMS prop. So what are the features of RMS prop? If you don't select the correct learning rate, then it will also oscillate around the minima. So it is very very important to initiate with the correct learning rate. Both ADA grade and RMS prop, they are sensitive to the learning rate because that eta is there. To overcome that, okay, we came to ADA delta, where we had adaptive gradients in for both that we have seen. Then to combine the advantages of momentum gradient descent with ADA, we came with the ADA. So like that, okay, you have to build up the story and your concepts. So there is another question. Suppose a data set has n samples and each sample has two features. Feature is 0, 1 Boolean. Assume that F1 is a sparse feature and F2 is a dense feature. Suppose further we apply stochastic gradient descent in this data and plot a contour plot of the loss surface and observe the movement of parameters, across iterations. Let W1 and W2 be the parameters corresponding to F1 and F2 respectively. Assume bias to be 0 for this question and the parameters are initialized to 0. In the contour plot of a loss surface, what is the initial movement expected to look like if W1 is plotted on the horizontal axis and W2 is plotted on the vertical axis? Okay, so here we are using a stochastic gradient descent. There is no, so in a stochastic gradient descent, so I will make again the same diagram. F1 W1 is F1 and F1 is sparse. This is W2. This is dense that I have made also. So in case of stochastic gradient descent, first of all, we have to understand that your update takes place with every data point. Okay. We take one data point, we update. We take second data point, we update. We make third data point, we update. So it is jittery. It is not smooth because one data point can be far away from the another data point. However, we are not using any ADA grade or RMS prop. So what will happen in first, it will go in the direction of the dense. So there will be more towards dense, and then finally it will converge to the minima for the sparse. I hope this is clear.
Yes, because it goes opposite the highest gradient, right?
Yes.
Delta. So okay.
So there are more updates for the denser one. So it will take first updates in the denser one with the jittery and then it goes. Whereas, for example, if we would have used ADA grade, for example, in this case, then it would have gone from here only. It would have gone,
Towards the minima, right?
yeah,
Directly towards. Right.
like this. Okay.
Right.
And in case of RMS prop, it would have gone and it would have gone ahead and then would have oscillated in case your learning rate is not correct. Okay. So that is. Now there is another question. For example, Adam takes more memory than Adagrad. Is it true? Adam takes lesser memory than Adagrad. Adagrad takes more memory than RMS prop. A vanilla gradient descent takes lesser memory than Adagrad. So how to solve this? Again, this is a basic concept. See, in Adam we have got beta 1 and beta 2. Okay, one is for momentum
Mm-hmm.
and another is for taking the gradient square wala. So you are keeping this memory also, betas also you are updating. Whereas an ADA grad you have got only, no, there is no beta,
No beta, right?
but you are carrying this memory W1, W2 square, all that. Okay.
V2, yeah, VT.
Adagrad takes more memory than RMS prop. No, in RMS prop there is a beta, so RMS prop will require more memory than Adagrad. Okay. Vanilla GD takes lesser memory than Adagrad. Yes, because in Vanilla GD we are not carrying any of this. So what I wanted to say, basically, all the questions I have gone through in the previous quiz papers on the week file, mainly the questions they have been asked on the concepts. Okay. So if your concepts are clear that how these algorithms are working, you will be able to answer those questions. Okay. We'll take another question. For example, this is a data set X, this is Y, and they have given that suppose we pass each of these samples to a sigmoid neuron. We know the sigmoid neuron. Suppose we initialize all the parameters values to 0.1, use the loss function this. Suppose further that weights are updated using a stochastic gradient descent algorithm for 5 iterations. Which of the following weights will get updated at least thrice with non-zero gradient? For example, this is W0, this is W1, W2, W3, W4, and W5. So which of the weights, there are 5 iterations they have taken place.
W1 से weight होगा ना, तो W0 is bias.
Yes, okay.
Right.
Yeah. So which ones will get updated? Which are denser, easy to see. We have been
Okay.
we have been covering that. Okay, denser parameters will
Oh, it's as simple as that.
as simple as that. So that's why I wanted to cover these questions. The question might look long, but if your concept is clear, it will will just take 30 seconds to answer that.
Okay. Okay.
Okay.
Cool. Thank you.
Okay. Okay. Then there is another question. Okay. Consider a function f w is equal to w plus 1 whole square. Suppose we want to find a value of w for which the function attains its minimum using iterative algorithms, namely gradient descent and Adagrad. The update rule of Adagrad is given. Assume n is equal to 0.5, v minus 1 is equal to 0, w0 is equal to 1. Select the correct statement from the following. Adagrad takes lesser number of iterations than vanilla gradient descent to converge.
Yes.
This will be true.
Yes, because it has momentum, no? So
Yeah. Okay.
history, right?
Yeah. Okay. There is another question. Assertion is that effective learning rate in RMS prop may increase or decrease,
Yes.
and the reason for that, this is due to the exponential averaging of the squared gradients options. So, which will be the answer for this? We have seen that in RMS prop, again, it remains Vt plus beta, but now this Vt which is there is equal to beta into Vt minus 1 plus 1 minus beta into Wt square. Now, depending on this Wt square, this Vt might increase, it might decrease, it might remain the same. So that's why the effective learning rate for RMS prop may increase or decrease, correct? This is due to the exponential averaging of squared gradient options. This is also correct. Okay, because this is happening due to this reason. Okay.
Okay.
Yeah. Okay, there is another question. Suppose that we modify the update equation of Adam optimizer as follows. We make mt is equal to this, vt is equal to this. So what they have done, they have removed the bias correction. Okay. Mt is equal to mt at by 1 minus beta t. This was there. So they have removed this.
Okay.
So what happens? They are asking that statement that using the modified algorithm will not converge due to missing bias correction term is true or false. So
still converge, no?
It will still converge. Yeah.
Right.
Okay. So that I had covered here. It is only we do the bias correction so that your initial updates which are there, they start from here.
Yeah. Right.
Okay, but still, your convergence will take place in both the cases.
Right.
Okay. So with that, I'm done with week 5. If you want, okay, we can take a 2 minutes break. We can have a glass of water before we move to week 6.
Right. And I'm the
Any,
only one talking. If others want to take the lead, please.
yeah, anyone, any doubt? Okay, Anadi, Rishabh, Anna, Sai, Teja.
No, like it's theoretical, so it pretty much understood everything.
Yeah, and it's a theoretical, and I'll suggest, okay, from my own experience, you build a story on that. Okay, cover, okay, see what is MGD, why we arrived at MGD, then why, what were the things for which we moved from momentum gradient descent to Nesterov accelerator. Okay, now why we wanted ADA grade? Okay, what was the basic reason? Now, when we came to ADA grade, what are its disadvantages? Okay, from to overcome those disadvantages, then we brought an algorithm called RMS prop. Now, what are the characteristics of that RMS prop? What is happening? Okay, then we came to ADA delta. So, what is something significant which we have achieved with ADA delta? So, basic concepts, okay, keep on building, build your stories, and then you will understand uh, quite nicely. Okay, I'll just take like a 1 minute break. I'll have a glass of water. Okay, I'll just come back. Okay, hi Puneet, I'm back. Hello.
Hello.
Hi, can we start with week 6?
Yes.
Yeah.
Yes.
Okay, okay. So, till now what we have covered the all the optimizers. Optimizers are the techniques by which we make algorithm more efficient, faster to converge, and we covered, okay, all the optimizers here before that. Now in the week 6, what we are starting is the something called regularization. And why do we need regularization? That we have seen during our machine learning foundation course, during machine learning practice also, that there is something called overfitting. That when we make a complex model and when we fit that model on our training data, so your training error might become zero. However, when you will deploy that model on your test data set, then it will have the MSC or whatever the matrix which you are utilizing to test your model. It will have more errors, I will say, more losses. So with that, professor has covered in the lecture that how we started that if we have got a simple model, for example, on the screen, on the left side, this red curve which is there, it might be the true function from where the data set is coming. And the blue is the one which our model is there, and we can see that it is a simple model. It's a linear model. So we can see the bias which is there, it has got high bias. That bias means that from the actual points, these values are very, very large. However, when you see its variance, how much it is varying, the variance is low. So we can say that simple models will have high bias and low variance. Now, what happens when we increase the complexity of the model For example, we make something like fx is equal to x cube plus 2 by 3x square plus 3x plus 4, then the model reaches, it tries to learn all the data points. So your bias which is there, it is low. But when you see its variance is very, very high for the complex data models. Okay, so that is, you have to remember from both examination point of view and understanding point of view, that simple model bias is low, variance is high. Oh, sorry, bias is high. I covered. Opposite. Simple, bias high, variance low. Complex, bias is low and variance is high. And how do you come to know about the complexity of a model? By knowing the polynomial degree. Higher the polynomial degree, more complexity of that model. Now from there, uh, in the lecture, this concept has also been covered in detail, and I will tell you there are very, very few places where you will find this explanation that why do we need regularization, and covered in such detail. So I'll request all of you to go through this, how the professor has covered that why this we came to this term which we have to, and then we use some lemma, and from there we arrived that we have to carry out a regularization. Okay, so here the same thing has been covered, that if model is becoming complex, high variance, this is simple model, high bias, and we want to be at this sweet spot. So how to do this regularization? So there are various ways. Regularization means that we are not allowing our model, to overfit the training data set. Otherwise, we know the neural networks that having enough number of hidden neurons. Okay, just give me 30 seconds. Hi, sorry everyone. Okay, there was a chaos at my place due to my dogs. Can you hear me?
Yeah, we can make out, but not the best.
Okay, now can you make out?
Yeah, please go ahead.
Okay, so I hope you have been able to understand this concept, that why do we need regularization. If you want, I will cover again what happens that if we have got a data set and we just train it on the training data, training only. Okay, so this is our data. And if we take a complex model, what it will try to learn all the points. So it comes, so we train in the neural network, we learn the weights. However, This data, when we deploy on the test data set, so this is the model we have deployed, but the points which are there, they are not from here. So that's why we want that model which we want to do, we want to regularize it so that it does not learn, exactly from every data set, and we make it less complex. Less complex means less number of polynomial degrees. So for example, if I learn a data model like this, and if I deploy this, then for example, a regression problem, then your mean square error will be lesser than the complex data model. That is the basic reason of the regularization. Mathematically, professor has covered train error, test error, empirical error, and he has arrived using that lemma with this value of sigma. This is the one which we have to take care. Now, the various regulation methods which are available, which we use, is the L2 regulation. We have used it in machine learning foundations. The second is the data augmentation. We augment our data set. We add some new data by manipulating the existing data. Third is the parameter sharing and time. This is generally done in the encoders. Adding noise to the inputs, adding noise to the outputs, early stopping. Then we will cover certain ensemble methods, basically the bagging, which again we have seen during MLF, and then how to utilize this ensemble method in a neural network. Now let's come to L2 regulation. So L2 regulation, we know that instead of minimizing only the loss, what do? We minimize something called alpha by 2 and the weight norms. This is a hyperparameter which is used, and when we do this, so what happens, we don't allow the model to learn only these data points which are available. We are adding this weight norm also. So gradient of LW remains gradient of LW. We take it becomes hyperparameter into W. Update rule remains this. Here a new this has come. Now I will try to cover it geometrically. That what is happening. So you see, this is the loss surface. The green ellipses which are there. These are the loss surfaces contours for the original loss. And this W star is the optimal weight vector which we have formed, which is minimize this. This red circle which is there, this is coming from the additional part from this sigma of Wi square. This hyperparameter which is there, it controls the radius of this circle. So higher the hyperparameter, more the radius. Less the hyperparameter, less the radius. And where this ellipse and this circle, they are joining, this is your new W tilde. That instead of having this W star, this is your weight vector, which is the final one. So due to this, what has happened? There are two things which have happened. First of all, this optimal W star which was there, which was in absence of regularization, it has been brought close to the origin. You can see it is coming close to the origin. Number one. So what happens? It will favor small weights. That weights will become smaller. Number two, when it is being brought closer to the origin, the parameters which were not relevant, they didn't get any updates, and only the important features which are there, they get more weights. So this is the geometric understanding of your L2 regulation. I hope I'm not clear. If you want, I can cover it again.
It is understandable, sir.
Okay, very nice, very nice. Then. Okay, so this L2 we have gone. Now between this L2 and This update, there is certain things which have been covered here regarding eigenvalues and Hessian matrix that you can go through only for the understanding part. Otherwise, this is the geometrical understanding of your L2 regularization. Now, if I ask you a question here, that if I don't do regularization, for example, then which error will be more, training error or test error?
Test error.
Okay, very nice. Okay, so then it is clear. Very nice. Now, second technique for the regulation is data set augmentation, where what we know that in neural networks we need lots of data. Now, if we, for example, we don't have that much of data, what do? So we generate more data from the existing data. For example, by rotation of an image, by blurring it, by shifting it vertically or horizontally, or by changing some pixels of that. So that's how we do data set augmentation, and generally it works well for image classification and for object recognition tasks. Intuition behind that is that only. I'll just cover. For example, if I had data of only this, and my model will only learn from this. So if a new image comes which looks like this, it will not be able. It will not be able to identify this. So why not to give more data of a different shifted. So that is the basic intuition of augmentation, this data. So again, you can see that if this is only one, then it will overfit only on these images. When we add more data, then it will not overfit. So again, that concept of regulation comes. The third technique is parameter sharing and tying. Parameter sharing is generally used in convolutional networks, which we will study in coming 7th or 8th week, wherein the same filter is applied at different positions of the image, or some weight matrix is applied on the different neurons. So then it is known as sharing. Parameters tying is generally done in autoencoders, where there is an encoder and there is a decoder, and the parameters which are there, they are tied. Tied means if I'm changing here, this also gets changed here. So that is also one of the technique of regulation. More regulation technique is we add noise to the input. So this is very, very similar to the data augmentation which we just saw now. That instead of overfitting on the existing data, we add a noise to that so that the model doesn't overfit. Then is adding noise to the outputs, that instead of having output, for example, this is 0, 1, 2, for example, for 2, this is the hard target. What we do, we add some noise everywhere and subtract that some of that noise from here. So this also acts as a regulation technique. Early stopping is a very, very useful technique which is used widely in most of the neural networks, and this is also a regulation technique. So how does it take place? We have got a training error, and we are also measuring the validation error. Now, if we define that, if, for example, for these many steps, for 10 iterations or 20 iterations, or we say a window that if my loss does not change by 0.001, then I will stop. This we have seen, okay, we do in the gradient descent also. We use a parameter called doll. So in the same case, whenever my validation error is not changing or has started increasing, I stop. Otherwise, what will happen if I don't stop? My training error will keep on becoming smaller and smaller, ultimately becoming 0. But we know that this is a case of overfitting. And in case of overfitting, my validation error will start increasing. So this is the point here I take a decision that I stop. Then we come to ensemble methods. Ensemble method, only bagging has been covered in the lecture. That bagging, we use different instances of the same classifier, and then we, for a given data set, we construct multiple training data sets by sampling with replacements. And bagging, when it works, if the errors of the model are perfectly correlated, then MSE is equal to V. If all the models are perfectly correlated, then the bagging does not help. So the models, it is very important that the models which you are, that the data set which you are selecting are different from the same data set. However, on an average, the ensemble will perform at least as well as its individual members. If there are 8 models we have got, if not better than the best, then it will be as best as the best of the model which has been trained. Now we know that in a neural network, it has got many hidden layers, many weight parameters, biases. So it is very, very computationally costly to use ensemble methods, which we have done in the MLP for our normal machine learning projects. So how to utilize the same concept in a deep neural network? So a technique called dropout is the one which is used in the deep neural network. So what happens in the dropout? For example, this is my input layer. This is my hidden layer. So what do we do? In the first instance, what do? We select only number of the neurons which will participate. So for example, in this iteration, only these many neurons will participate. And this is decided by a parameter called P. And this P can be selected for different hidden layers. So here I select, for example, 1, 2, 3, 4, 5, 6, 7, 8. I select P is equal to 0.5. So only 5 will be selected. Here, for example, P is equal to 0.4, 4, 5, 6. So here only 4 will be selected. Generally for the input layer, P is slightly higher. So we select, for example, 0.8. So in one iteration, for example, or if you are doing a mini batch for one portion of the data set, only these neurons, they have participated. So only the weights of these neurons will be updated. In the second iteration now, depending on P, now different or the same neuron might get selected. So what is happening effectively? So next iteration we have selected this. Now weights get iterated, weight gets updated. Now in the third iteration, again some different neurons will get selected. So what we are achieving the same effect like the ensemble method. That for every iteration we are training a new model. Okay, is this clear? Okay, any doubt in anybody's mind regarding this dropout?
So dropout means instead of creating ensembles from data, you actually create ensembles from your network neurons.
Yes.
Yeah. Okay.
Yes. Okay. So in every iteration or any mini batch, your different neurons, weights are getting updated. So that is basically dropout. Now, important things to remember that for every hidden layer, you can have different P's, probability. And when you do at the test time, so the neuron which was selected, for example, it was always present, then you multiply its weights by the P. PW1, PW2, PW3, PW4. And at training time, present with probability P. Okay, for example, if it was 0.5, then it was present 50% of the times. And at the test time, you update its weights by P. This is the concept of dropout. This I have explained, dropout. Now with this, now this is the final thing which is happening due to regulation. So I'll expand my screen. On the left side, if you see, this is the, if we don't do the regulation, this is the loss surface which looks like. You can see so many zigzags. Your gradient might get stuck somewhere. It will have got many depths. And when you do the regulation, it smoothens your loss surface. So you can see this is the effect of your regulation. Now, grouping regulation techniques, here you can see we have got data augmentation, we have got noise injection, dropout, CNN, weight sharing, we have got pooling. Then SGD and is also you can consider as a optimizer, and it is also one of the regulation. And then we use impose penalty cost, which is L1 regulation and L2 regulation. Early stopping we have seen it is a one form of regulation. Now we come to week 5 PAs. If can we go to the questions which you have not been able to solve, or we solve all the questions, or I cover the concepts?
This is week 6 PA or week 5? Week 6, right?
Week 6. Week 5 does not have any PA.
Right. The title. Okay.
Yeah. Okay, sorry, my mistake. So this is, I was thinking week 5 will also have.
Yes, we all go through this.
Yeah. Okay. So the figure below shows a set of points from a training set. So these are the points, all at 0.5. So the question is that a statement using a simple model fx is equal to W0 plus W1x is sufficient to make the testing error 0. It is said it will make 0 is true if the true function that generated the data point is fx is equal to 0.5. So is it true or false? Anyone?
This is true.
And what is the reason?
Because if the generated function is the same as like distribution, then the testing will also lie on this same function, and
yeah,
we can probably see that it's fx equal to 0.5.
Okay, so if your true function, for example, was fx is equal to 0.5 plus some noise, if we take 0.001, then this would not have been true. Is that correct?
Right, that would have become the error then, right?
Yeah. So then it would not have given 0. It would have got some loss. Second, it is false if the true function that generated the data function is of sine of kx. So this we can see this is also valid.
Yes.
Okay, because if your true function was like this, then your loss would not have become 0. Okay. So it's a concept question. Now, second is consider two models.
So I'm just out of curiosity.
Yeah.
What if the sign, if all the points landed on the sign value, if the wavelength matched precisely?
See, sine will never be like this.
No, I'm saying the intersection points. If the points lie on the curve, so the curve, the sine, if these points are all equidistant,
yeah,
there might be a sine curve.
Yeah.
I don't know if the points are equidistant, so we will check.
No, they are equidistant. But what will happen? Okay, for example, I'll just cover it here. In the
Suppose all of them are at the
Okay. So what will happen? Your true function is f dash x, from where it is coming is sine of kx.
Right.
Okay. And you have estimated the model as fx is equal to w0 plus w1x. Okay. This is your trained data set. For example, this is your trained data set. This is your trained data set. And what you have learned, f0 is equal to w0 plus w1x, means it is a straight line. Okay.
Okay.
Now when your test data set comes, it will be following something like this. Okay, this is also followed. So here also your lines will be, because it is coming from this function.
Right. So this part I'm good. Now I'm saying that if you take any image of a sine curve,
Yeah,
right, and let's say the sine curve is longitudinal on your x-axis, so yeah.
it is like
And
this.
if my data points are exactly where y is 0,
Yeah. So
right?
yes.
Yeah. I'm just
So
saying that. So there is
yeah,
a condition that should be there, right?
yeah,
So we have to check that.
yeah. But see, when you take the data points, I've understood your this. You are saying that, for example, this is the sine wave,
Right.
and your test data points which are there, they have come here only.
Yeah, some fluke that they've come on the curve
Oh,
for
okay.
training, right?
So that will be a fluke only.
Right, right.
Yeah. Okay. But I hope again this concept became clear again. That
Yes, yes.
test error and training error. Okay. So consider two models, f1x is equal to w0 plus w1x, f2x is equal to w0 plus w1x square plus wx5. Which of these models has higher complexity? So this we know,
Higher the,
higher the polynomial degree.
yes. It's the Taylor series, same thing we had done, right?
Yeah, higher the
More. Right.
complexity. Okay. Now this I had solved myself. Consider the surface of a function. Function has been given. I will zoom it. Minus e to power minus w square plus b square plus 1. This is a loss surface. And the question, suppose that w star and b star are the values for which the function attains its maximum, then choose the correct statements.
Minimum.
Minimum. Okay, this is, yeah.
Right.
So just you have to take a function by w, then you have to take w by wb, find w star,
Okay.
find b star, and then find the value uh, of w star b star वो तो 0 हो जाएगा, and you can find the
Mhm.
L also w star b star. Okay. So,
Okay. Okay.
so this is straightforward. Okay. The statement that L2 regularization penalizes all the parameters in the network equally.
No.
Yes.
No,
Okay.
for more significant, it penalizes this, I guess.
Okay.
Yeah, it
So
penalizes the fringe ones, closer.
Yeah,
Yeah.
fringe ones.
yeah. So remember this, okay? This origin which is there. Okay. This is your regularization one, and this is your loss surface, and where it is meeting with this. This is your w tilde, and here it will penalize the parameters which are not important. Okay. Now consider the problem of recognizing an alphabet of English language in an image. There are 26 alphabets in the language. Therefore, a team decided to use CNN network to solve the problem. Suppose that data augmentation technique is being used for regulation, then which of the following transformation on all the training images is appropriate? So we have seen cropping will be one.
Yes,
Is that
cropping
all?
will-
Yeah. Rotating the image by plus minus 10 degrees.
Yeah,
Translating image by 1 pixel in all direction.
Yeah.
yeah.
This one, is it valid?
No, it will. It might change the number itself.
Okay, so this is not valid only due to one reason, that we have got 6 and we have got 9.
Yeah.
And when we do 180 degree of 6, okay, it becomes 9. Okay, so due to this reason only 180 degree. Otherwise, can we do 150 degree, 90 degree? Okay, all are valid. Only 180 degree, there is a case of 6 and 9.
But won't the 150-degree between 90 to 180
Yeah.
will look like more like
Yeah,
tilted
so
90?
Upside down tilted. Yeah.
yeah, so I had just covered okay, the concept wise.
Right.
Otherwise,
Right.
all other is okay, like 90 degree, 270 degree, they are valid. Okay. Only due to this 6 and 9, your 180 degree is not valid. Then suppose that we apply dropout regulation to a feed-forward neural network. Suppose further that mini batch gradient descent is used for updating the parameters. Choose the correct statement for the following statement. The dropout probability P can be different for each hidden layer.
Yes, but
Yeah.
how does mini batch make a difference?
Mini batch just meaning is that there are 10,000 data points and we are feeding one by one. Okay, 1,000, then another 1,000, another 1,000. Okay, and
Right, but the dropout probability P can be different is for all anything, right? Any of this.
it is generally chosen hidden layer wise.
Okay, right.
Okay. Batch gradient descent cannot be used to update the parameters of the network. This is false. It can be used. The weights of the neurons which were dropped during the forward propagation at Tth layer will not get updated during the T+1 iteration. Is it true?
Don't know. Depends.
Yeah, it depends. Okay. It can get selected here also, and it can get selected in the second also. Okay,
Right.
it depends on the probability. So this is not true. Dropout with P is equal to 0.5 acts as an ensemble regularizer. Yes.
Yeah.
Because dropout itself came to take the advantage and to resemble something called ensembling.
So unless P equal to 1 means all of them are getting selected, then it's no use.
Yes. You're right. Okay, so with that piece I have finished. Okay, and just to cover certain points, because there is a question in your GA where there is a question on the Hessian matrix.
We are doing eigenvectors again.
I think there is a question in your GA for week 6. So that's why I just thought, okay, I'll revise the eigenvalues and eigenvectors.
I have forgotten this.
Yeah. So just taking a simple this A is equal to 2, 1, 1, 2. This is a matrix. Then we know that for eigenvalues, then determinant of A minus lambda into I is identity matrix becomes 0. Okay. So we take 2 minus lambda 1, 1, 2 minus lambda is equal to 0. We get eigenvalues, we get 3 and we get 1.
Okay.
Now to find the eigenvectors, what happens? Now A minus lambda I into eigenvector, it becomes 0. Okay.
Oh, yeah, right.
So for lambda 1 is equal to 3, this becomes this. And from here, V1, V2 we find. So first eigenvector becomes 1, 1. So for lambda 1, eigenvector is 1, 1. Then we take lambda is equal to 1, then it becomes 1 minus 1. So this I just thought, okay, I'll keep here, okay, just to revise, okay. So eigenvectors we have got 1, 1 and 1 minus 1.
Should we revise this for quiz and exam? Final time?
No, they will not ask. They will not ask.
Okay. Just for the graded, right?
Just for this.
Okay.
And then second Hessian matrix. So Hessian matrix is what? Is nothing but here. If there is a function, for example, f(x) of y, then Hessian matrix is w square f by wx square, and it's a symmetrical matrix. Y here it becomes w square f, wy wx, and w square f wx w. Okay. And just go through that. Okay, I've included. I'll share this document. Okay, somewhere I'll convert it to PDF. Okay, that what are the characteristics of a Hessian matrix? Because Hessian matrix has been used again one of the. So this I have given one example, and what are the characteristics? It is a symmetrical plus it gives an idea about the local maximum, local minima, or a shadow point.
Right.
This was covered. So if the determinant of H Hessian matrix is greater than 0, and the first element is greater than 0, that is delta square by f by dou x square is greater than 0, then it is local minima. If d is greater than 0 and this is less than 0, then it is local maximum. And if d is less than 0, then it is a saddle point.
Yeah.
And I have solved one more question.
Yeah, this is from our MLF.
Yeah, this is from MLF. Okay. So with this, gentlemen, I have finished. Okay, in case you have got any doubt, okay, any question, you can ask me. And how was your quiz one? I saw the question paper after the quiz, and I will share with you. Your paper was much easy, concept wise. It was a good paper. I think it did not have any error also in case of the answer keys.
So for me,
the revision session You helped before the exam. That really helped. I got full marks.
My thoughts exactly. So
Yes.
yes, your session helped, and I hope you continue doing these. So I think I was able to answer all the questions. I was not stumped by any of the questions.
That's so cool. So most likely we will have our sessions every Thursday.
This one
Yeah,
also on Thursdays. So the live session timing, same time.
yeah, live session timings. Okay, we'll
Okay.
have at that time.
Okay.
Chalo, then shall I take a leave? Okay.
Okay. Thank you. Thank you,
Thank
Nitin
you.
sir. Thank
Okay.
you.
Have a nice day. Bye bye.
Bye, guys.
Good night.
Bye.